Assalamu alaikum and very good morning. Welcome to EBT318 Surface Engineering online class. Ladies and gentlemen, today, we will proceed with surface engineering characterization and testing. To understand the benefits that surface modifications provide, and ultimately to devise better ones, it is necessary to study the physical, mechanical, and chemical changes they cause. This topic surveys classical and leading-edge developments in surface structure and property characterization methodologies. The primary emphases are on the use of these techniques as they relate to surface modifications, thin films, and coatings, and tribological engineering surfaces, and on the implications rather than the instrumentation. Before we proceed to the next slide, our class code is surface. Characterization of engineering surfaces. The properties of modified engineering surfaces in practical applications can be determined by material and surface analytical techniques. Material and surface analyses are evolutionary disciplines. A number of analysis techniques are available for studying modified surfaces, thin films, and coatings from the atomic and electronic levels to macroscopic, engineering component levels. Such techniques include a variety of physical, chemical, material, and mechanical characterizations. They can provide information that will allow one to select the materials, surface treatments, surface modification techniques and conditions, thin films and coatings, and environments best suited for a particular technical application. Look at the picture here. It is the 3D image of surface profiler on orthopedic hip implant after surface conditioning process. In the past year, the advancement in science has taken place mainly with the discovery of new novel materials. Characterization is an important step in the development of exotic materials. The complete characterization of any material consists of phase analysis, compositional characterization, structural elucidation, microstructural analysis, and surface characterization, which have strong bearing on the properties of materials. This has led to the emergence of variety of advanced techniques in the field of materials science. The major characteristic parameters of surface layer to be considered can be listed as follows. In electrical characteristics, there are conductivity for conductive films, dielectric constant, dielectric loss, dielectric strength, electromigration, permittivity, polarization, radiation hardness, resistivity for resistive films, and stability under bias. In thermal, there are coefficient of expansion, stability or drift of characteristics, temperature variation of all properties, thermal conductivity, thermal fusion temperature, volatility, and vapor pressure. Mechanical characteristics consist of adhesion, anisotropy, density, ductility, elasticity, fracture, hardness, intrinsic, residual, and composite stress. In term of morphology, there are conformality or step coverage, crystalline or amorphous, crystal light orientation, microstructure, planarity, structural defect density, and surface topography. For optical characteristics, there are absorption, birefringence, dispersion, refractive index, and spectral characteristics. In magnetic properties, there are coercive force, permeability, and saturation flux density. Lastly, chemical characteristics, there are carcinogenicity, composition, corrosion and erosion resistance, etch rate, hygroscopicity, impurities, impurity barrier or gettering effectiveness, reactivity with substrate and ambient, stability, thermodynamic stability, and toxicity. Despite all the characters and properties of thin film or surface layer, we will only focus on some popular techniques as follows. Thickness measurements. Optical absorption. Scanning electron microscopy, SEM. Transmission electron microscopy, TEM. Energy dispersive analysis, EDS. Atomic force microscopy, AFM. Photoelectron spectroscopy, XPS. Raman spectroscopy. Ellipsometry. Photoluminescence. UV visible spectroscopy. Fourier transform infrared spectroscopy, FTIR. It is noted that, SEM, TEM and EDSR actually has been covered in the syllabus of other subjects such as material or metallurgical characterization, so in this topic we will only briefly explain these three techniques. Thickness measurement. The thickness of the film is the most significant parameter that affects the properties of the surface layer or thin film. It may be measured either by in situ monitoring of the rate of the deposition or after the film is taken out from deposition chamber. Technique of the first type, often referred to as monitor methods, generally allow both monitoring and controlling of deposition rate film thickness. Any known physical quantity related to film thickness can be used to measure the thickness. The method chosen should be convenient, reliable, and simple. One of the most convenient and advanced methods for determining film thickness is surface profilometer method. Basically, profilometer is a measuring instrument used to measure a surface's profile, in order to quantify its roughness. Vertical resolution is usually in the nanometer level, though lateral resolution is usually poorer. This is the example of surface profilometer software, which provide interactive 3D maps, quantitative topography information, intuitive measurement navigation, and built-in statistics, control charting, and pass or fail limits. There are two types of profilometer that are contact profilometer and non-contact profilometer. In contact profilometer, generally, it called as stylus-based profilometer. A diamond stylus is moved vertically in contact with the sample and then moved laterally across the sample for a specified distance and specified contact force. A profilometer can measure small surface variations in vertical stylus displacement as a function of position. A typical profilometer can measure small vertical features ranging in height from 10 nanometers to 1 millimeter. The height position of the diamond stylus generates an analog signal which is converted into a digital signal stored, analyzed, and displayed. The radius of diamond stylus ranges from 20 nanometers to 25 micrometer, and the horizontal resolution is controlled by the scan speed and data signal sampling rate. The stylus tracking force can range from less than 1 to 50 milligrams. In non-contact profilometer, an optical profilometer is a non-contact method for providing much of the same information as a stylus-based profilometer. There are many different techniques which are currently being employed, such as laser triangulation, triangulation sensor, confocal microscopy, used for profiling of very small objects, and digital holography. In order to measure the film thickness, a step has to be made on the film, either by doctor blade or by dipping the film in acidic medium. While measurement, the stylus is scanned over the step at various positions, or simply called as step, and the average step height will prove the film thickness. Roughness is a measure of the texture of a surface. It is quantified by the vertical deviations of a real surface from its ideal form. If these deviations are large, the surface is rough; if they are small, the surface is smooth. Roughness is typically considered to be the high-frequency, short wavelength component of a measured surface. Now, let's take a look at the video clip on thickness or surface roughness characterization techniques. First, we start with laser triangulation by 2D/3D laser scanner equipped by laser profile sensor. Now, we go to a new model of confocal microscopy from Zeiss.
SmartProof 5 Wide Field Confocal Microscope. 10 highlights in 90 seconds. Combine fast topography measurements with simultaneous wide field imaging and documentation. Acquire 3D images of surface structures and evaluate the raw, unprocessed data for results you can trust. Analyze surface roughness optically, without contacting or damaging the sample surface. Aperture correlation technology yields both high optical resolution and fast acquisition speed. Load the stage with large and heavy samples or multiple holders and fixtures for greater productivity. The robust and fully integrated design minimizes vibrations to enable use on the shop floor. Automation ensures consistent results and increased efficiency, independent of user experience. Harness the power of data compatibility in connected labs and easy operation even for novice users. Measure geometrical parameters and carry out roughness analysis based on industry standards. Enable correlative workflows and separate imaging from post-acquisition analyses.
And lastly, a short video on principle of digital holographic microscopy.
After more than 10 years' research at the Swiss Federal Institute of Technology using the same phase interference, scientists registered the holographic image in a digital camera, which then feeds the information into a computer program. The numerical reconstruction process permits immediate quantitative access to intensity and phase, topographic measurements accurate down to the nanometric scale, and an immediate, real-time follow-up surveillance of the sample evolution.
Anyhow, amongst different methods for measuring the film thickness, the weight difference method is simple and convenient. Thickness T is measured using the relation T equals m/a rho b, where m equals the mass of the film deposited, a equals area of the substrate, rho b equals the density of the material in the bulk form. The mass m of the film has been measured by using a single pan microbalance as depicted in picture here.